Remember the first time you heard about the planetary model of the atom? Think of that time you first pictured tiny electrons revolving around a nucleus, just like how planets revolve around the sun. Did you ever stop to ask yourself, who came up with the idea to picture the atom the same way we picture our solar system? Well, it was none other than Rutherford himself. He and his colleagues proposed an entirely new model of the atom through the alpha scattering experiment. So in this video, we will dive into the how, what and why. How the experiment was conducted, what observations were seen, and why did they even occur. This experiment involved throwing a stream of alpha particles onto a very thin gold foil, and then observing how the alpha particles deviated because of the foil. Now you might be wondering, what's so special about gold? Well, it is a stable and unreactive element, and so it won't change chemically when alpha particles strike it. Another interesting thing you might have noticed is that the detector itself is curved. This is done so that all possible deviated paths of alpha particles can be considered. When this experiment was first conducted, 3 remarkable observations were made. Majority of the alpha particles managed to pass through without any deviation. A few alpha particles were able to pass through with slight deviations in their path. But what was most alarming was that even fewer alpha particles deflected at angles greater than 90 degrees, meaning these particles somehow bounced back completely. Now let's analyze each of these observations and justify their occurrences. The first observation tells us that majority alpha particles did not deflect at all. This means that most of the alpha particles must have encountered empty space where there were no interruptions. Therefore, majority of the atom must contain empty space. The second observation reminds us that the atom cannot be entirely empty. The fact that some alpha particles deflected a little implies that there might be something in there that repelled the alpha particles. And since we know alpha particles are positively charged, then that automatically means this special center should also be positively charged. This quote-unquote center was eventually called the nucleus. Finally, the third observation indicates that very few alpha particles did a head-on collision with the nucleus, which was severe enough to prevent them from passing through. This tells us 2 things about the nucleus. 1. It is extremely small, which explains why so few alpha particles were able to repel this much. And 2. It is extremely densely charged, which explains the massive amounts of repulsion. In all of this, you might be wondering, where on earth did the electrons go? Well, even though the experiment did not directly give evidence of these electrons, scientists did know that all atoms are neutral, meaning they should have both positive and negative charges. Since it was already proved that the nucleus must be positively charged, Rutherford was able to infer that the electrons must be outside of this nucleus, and so he proposed that they must be revolving in their fixed orbits. And voila, we have our planetary model of the atom. Although this model had its flaws, it was still a massive step in understanding the structure of the nucleus, which was an important gateway to better understand complicated things like nuclear decay and even the strong nuclear force. And so that wraps up this section. Let's do a brief overview of all that we have covered. In this lesson, we went over the alpha scattering experiment, in which Rutherford and his colleagues fired alpha particles at a thin gold foil. They observed that majority of the alpha particles passed through undeflected, meaning that the majority of the atom must be empty space. Some alpha particles deflected by angles less than 90 degrees, meaning that the center or the nucleus must be positively charged. And the very few alpha particles that bounced back completely felt head-on collisions with the nucleus, suggesting that the nucleus must be heavily charged and very small in size. All these observations and results led us to the planetary model of the atom that we all know and love.